We are moving on from our discussion of solubility equilibria on to acid-base equilibria. That's our second specialty type of equilibria system that we're going to study. So, to remind you of old definitions that you should have come across last semester, an acid, according to the Bronsted-Lowry definition, an acid is a proton donor and a base is a proton acceptor. What the heck is a proton? Well, a proton is a subatomic particle, meaning a thing found in the nucleus. But when we talk about proton donation, we're really talking about a hydrogen atom that has lost its electrons, so period. So you may remember that a hydrogen atom has one proton and one electron, a neutral hydrogen atom. But when you lose that electron, it becomes a positively charged species. It's really just a bare proton at that point. So when we talk about protons being donated and accepted, we're talking about H's being donated and accepted. Okay, so in this system here, which species donates an H? Both of them have H's. There's H's connected to carbon here. H is connected to oxygen, officially, according to the Lewis structure here. This thing has two H's, and over here it's got one. Ooh, it donated, so it's an acid. This guy is an acid. Must mean this one is the base. And in addition to those terminologies, we have to name conjugate things also. The thing that is the acid becomes the conjugate base on the other side of the equation. The thing that is the base becomes the conjugate acid on the other side of the equation. All right, this has no H's, so it can't be a Bronsted acid. So it must mean this guy is my acid, which means this one is my base. This is my conjugate base because it's after the acid has lost its H. And this is my conjugate acid because it's after the base has accepted a proton. There's also an Arrhenius definition of acid. An Arrhenius acid must react with water, and it always produces H3O plus in aqueous solution. And an Arrhenius base always produces OH minus when it's in aqueous solution. So these definitions of Bronsted-Lowry are what we're going to use most often, but we'll see Arrhenius on occasion also. Before we move on to the next thing, I want to point out that down here, when this thing's got a charge, a negative charge is likely to be a base. It's possible it could be an acid in some circumstances, not this one because there's no hydrogen, but a negative charged thing is likely to be a base. A positively charged thing is likely to be an acid. So this guy is the conjugate acid because he's on the product side of the equation. But that's a couple things to note. Positively charged things likely to be acids, negatively charged things likely to be bases, but there are more rules than that. We're just giving you a little shortcut to start out with. How do acids and bases relate to equilibrium? Well, remember the magnitude of a K value, how big a KEQ equilibrium constant is, tells you how much products or how much reactants, how far forward does the reaction go or not go. So this guy is a small K value, so that means that this equilibrium process does not produce much product. This middle one has a greater than 1 Ka. It means this produces a lot of product. This bottom one has the smallest K of all. It produces the least product. So how does that relate in what we're going to discuss? Well, it means that I can rank these acids in terms of strength. As you may recall, strong acids dissociate completely. So to be strong, it means fully dissociated. And so fully dissociated acids are going to have large K values. So I can actually look at these three values and say, this is my strongest acid, if I'm ranking them on a spectrum. This is the middle. It's officially weak, but it's the middle. And this is the weakest acid. And all I did was look at the K values to know that, because they're all written as these guys are acids, and they produce H3O plus in solution, and their conjugate base is present also. All of them react with water to produce H3O plus and give their conjugate base. Okay, so where are we going here? So I also wanted to say that this is HCN reacting with H2O to yield H3O plus and CN minus. That's the Arrhenius definition, reacting with water to yield this thing. Sometimes we take a shortcut and write HCN breaks apart into an H plus and a CN minus. And free-floating H plus is not something that actually exists in aqueous solution. Water is going to react with an H plus type species to always yield H3O plus, but sometimes we write it in this shortcut way anyway because it's easier to understand sometimes without keeping up with water and H3O plus stuff. Okay, of the species shown, which ion or molecule is the strongest base? Well, we've already listed that this is the strongest acid. How do acids and bases relate? The stronger the acid, the weaker the conjugate base. I feel like you should probably write that down. The stronger the acid, the weaker the conjugate base. It's all a spectrum. So as acids get stronger, their conjugate bases gets weaker. So a weak acid, a super weak acid, is going to have the stronger conjugate base. So we've already listed this one as the weakest acid. That's this HCN is the weakest acid. So it means CN minus is going to be my strongest base. Remember, equilibrium reactions can be considered forward or backwards. So we can rank these reactions according to acid strength, or we can think about them in reverse and talk about base strength. That would be 1 over our given K values to think about base strength. Okay, moving on. Some acids dissociate completely in water. And if they dissociate completely in water, we call them strong. And if they dissociate completely in water, we use a limiting reactant, straightforward arrow, and only a straightforward arrow, and we get a K value that's big, a K value that's greater than 1. This is a really giant K value. The bigger the K value, the stronger the acid. Some acids dissociate completely, but really only 6 that we have to learn. Most acids only dissociate a little, and they give you K values that are less than 1, small K values. If it's a weak acid, we write it as an equilibrium expression, but we can break it down just like we broke down our HCl up top. It's just the type of arrow that we use is different. You must know the 6 strong acids I'm about to walk through. HCl is one of them. Yep. HCl is one of them. HBr and HI, those are easy to remember because it's the 3 halogens, 3 in the same group on the periodic table. HCl, HBr, HI. Nitric, perchloric, sulfuric. Nitric, perchloric, sulfuric. And sulfuric is really only strong to dissociate the very first H. We don't lose both H's as a strong thing. The first one comes off completely, and then the next one only comes off when you force it off. We'll see what that means later. There's our names of them. There are 6 strong acids you must know. I hate memorizing things, so I don't assign lots of things for you to memorize, but there are 6 strong acids that you must know. You must know the formula, the name, all kinds of things about these 6 strong acids. Okay, so a picture that we should keep in mind when we think about acids. If I pump HCl, which is actually a gaseous thing, if I pump gaseous HCl into water, it dissociates completely. Whatever amount of HCl I added, it's a 1-to-1 ratio of H plus and Cl minus that I get out of it. You see no intact HCl molecules. There's an H3O plus, H3O plus, H3O plus, H3O plus, H3O plus, but there are no HCl molecules left. There's a Cl minus, Cl minus, Cl minus, Cl minus. HF is a weak acid. What that means is when you put HF in solution, a little baby amount dissociates to make an H plus and an F minus, but most of the HF stays intact. Here's an HF, and another HF, and an HF, and an HF, and an HF. There's 1 dissociated F minus and 1 H3O plus from that thing because it's a weak acid. Weak. So if I had something like 0.7 molar HCl, that goes into solution to give me 0.7 molar H plus in solution and 0.7 molar Cl in solution, chloride in solution. It dissociates completely. It's a limiting reactant kind of thing. Every one of these that goes in solution creates one of those. If I have 0.7 molar HF, it does not dissociate completely, and I have a very small concentration of H plus. I have to use an equilibrium table to figure out what my small concentration of F minus and H plus are. Anytime I have a weak acid, I have to use an equilibrium table to figure out the concentrations of the ions in solution. Are you ready for this? If I have 0.7 molar acetic acid, number one question, is acetic acid strong or weak? Weak. Why is it weak? Well, I have memorized the 6 strong acids, and it's not one of those. That's exactly how I know. I do not memorize a list of weak acids. It's pointless. There are too many of them. I know that acetic acid, this guy, is not on my list of the 6 strong acids, therefore it's weak. Weak! So I need to do an equilibrium table to figure out the concentration of H+. I'm going to start with 0.7 molar, this stuff. My initial concentration is 0.7 molar. None of this, none of that. I'm going to lose some, I'm going to gain some. And my equilibrium concentration, we'll put it in terms of X just because this is our first rodeo with this guy. Looks like this. So my K expression is CH3COO minus times H plus divided by CH3COOH. And this is officially called a Ka because it's an acid dissociation constant. An acid dissociation constant because I'm starting with an acid and yielding H+. Remember, it was only a KSP when it was starting with a solid and dissociating into ions. It's only a Ka when I start with an acid and have H+ as a product. It is not Ka if H+ is a reactant. It's Ka if H+ is a product. Okay. Maybe I've preached enough. I plug in my values. I got X times X. That's X squared over 0.7 minus X. And I set that equal to the Ka value. It's a Ka. Not a pKa, but a Ka. So that becomes X squared over 0.7 minus X equals 1.8 times 10 to the negative 5. And then I do all my solving and have to do the quadratic equation? Question mark? No quadratic equation is required because K is small. I can assume X is small, so I can completely ignore the X that's being subtracted from my 0.7, because if X is small and you subtract a very tiny number from 0.7, it's still going to round off to be 0.7. So X squared over 0.7 equals 1.8 times 10 to the negative 5. And I don't really know why I'm writing out all the steps, but X squared would then equal 1.26 times 10 to the negative 5. Square root that thing. X equals 3.54 times 10 to the negative 3. Okay. The question back there was, what's the concentration of H plus in 0.7 molar acetic acid? Well, the concentration of X plus is equal to, concentration of H plus is equal to X. So the concentration of H plus is 3.54 times 10 to the negative 3 molar. Done. One thing that I maybe should have said prior to now that I didn't say, we're going to go back and explain now. If I had written this equation for my dissociation, H3COO minus yields H3O plus, I would have written a KC that was CH3COO minus times H3O plus over CH3COOH times H2O. But water does not really have a variable concentration. It's not really going to change. Water has an established concentration of 55 molar. That's a pretty large number. So if I take Kc and multiply by the concentration of water, I get CH3COO minus times H3O plus over CH3COOH. Well, Kc times 55 molar, that's really why we end up calling that Ka. It's officially a Ka when it's Kc times 55 molar, which is the concentration of water. I feel good because I've said that once. If you didn't get it or don't understand why, I apologize, but it is what it is. All right. A little tiny bit more that we need to memorize, unfortunately. Strong bases release hydroxide in solution. There are some strong bases that you need to memorize. We've learned these as soluble salts. Sodium hydroxide is soluble. It dissociates completely in solution to a sodium plus and a hydroxide minus. When you add water, sure. There's no H3O plus kind of stuff on this side because it's hydroxide. We put it over the arrow this time so that we don't have to keep track of it. Potassium hydroxide is another one that dissociates completely. Barium hydroxide dissociates completely. Note, there are 2 hydroxides in this guy. Some strong bases that you need to know. Lithium, sodium, potassium hydroxide. Those are alkali metals. Calcium, strontium, barium hydroxide. Those are alkaline earth metals. These are strong, means dissociate completely. So if you start out with something that's 0.14 molar sodium hydroxide, you have 0.14 molar hydroxide in solution. You also have 0.14 molar sodium. All right, the end. That's the beginning of acids and bases. We're going to study acids and bases for a long time. So if you get good at the definitions now, you'll thank yourself later. Goodbye.